So this is a final example to illustrate dynamic programming. So we look at the problem of matrix multiplication. So if you remember how matrix multiplication works, you have to take two matrices with compatible entries, and then we compute a new matrix in which for each entry there, we have to multiply a row here by a column of the same length and add up the values. So if we have a matrix which is m by n, then this must have n times p, right? So that we have a final answer which is m times p. So in the final entry, we have to make mp entries in the final product matrix, and each of these entries requires us to compute the sum of these n entries. So that takes us order n time. So with total work is usually easy to compute as m times n times p. So a, b, I, j is this long sum, and this sum has 1, 2, 3 up to n entries. So computing matrix multiplication for two matrices has a very straightforward algorithm, which is a triple nested loop which takes order m times n times p. If all of the dimensions are the same, this is an order n cubed algorithm. Now there are more clever ways of doing it, but that's not the purpose of this lecture. But the naive, straightforward way of multiplying two matrices is m times n times p. Our interest is when we have a sequence of such multiplications to do. So supposing we want to multiply three matrices together, A times B times C. Then it turns out it doesn't matter whether we first multiply AB and then multiply C, or we first multiply A and then multiply BC. Okay, A times BC, because this is stated as the associativity property. The order in which we group the multiplication doesn't matter, just for normal numbers. If we do 6 times 3 times 2, it doesn't matter whether we do 6 times 3 first or 3 times 2 first, finally the product is going to be the same. So the bracketing doesn't change the answer, the final value is the same, but it turns out that it can have dramatic effects on the complexity of computing the answer. Why is this the case? So suppose we have these matrices A, B and C, and A and B have these columns and rows. So A is basically got 1 by 100. It just has one row and 100 columns, and B has 100 rows and one column, and C has again one row and 100 columns. So these are matrices which look like this. Now what happens is that when I multiply B times C, okay, then I get something which is 100 into 1 into 100. Okay, so we'll get an output which is a 100 by 100 matrix. So that has 10,000 entries, so it's going to take us 10,000 steps. Now when I multiply A by this, I'm going to get 1 into 100 into 100. That's another 10,000 steps. So if I do A after I do BC, then I do 10,000 plus 10,000, so I do 20,000 steps. Now if I do it the other way, if I take A times B first, then this whole thing collapses into a 1 by 1 single entry. So I get 1 into 100 into 1. In 100 steps, I just collapse this row and this column into a single entry. That's like computing one entry in a matrix multiplication. The resulting thing is exactly that one entry. Now I have this one entry, and again I have to multiply it by this thing, and that will take me, for each of the columns in this, I will get one entry, so that will take me 100 steps, right? So I take 100 steps to collapse this A into B into a single cell, another 100 steps after that to compute that product into C. So instead of 20,000 steps, I've done only 200 steps. So this is the way in which the sequence of multiplications, though multiplication is associative and it doesn't matter what you do, you'll get the same answer. The sequence in which you do the associative steps can dramatically improve or worsen the amount of time you spend doing this. So in general, we have a sequence M1 to Mn, okay, and each of them has some rows and columns. And what we are guaranteed is that each adjacent pair can be multiplied. So R1, C1, R2, C2, the first two are such that C1 is equal to R2. The number of columns in the first matrix is equal to the number of rows in the second matrix. Similarly, C2 is equal to R3 and so on. So these dimensions are guaranteed to match. So the matrix multiplication is always possible. Our target is to find out in what order we would do it. So we can at best do two matrices at a time. We only know how to multiply A times B. We cannot take three matrices and directly multiply them. So if we have to do three matrices, we have to do it in two steps, A times B and then C, or B times C and then A. Now same way with n matrices, we have to do two at a time, but those two at a time could be complicated things. I could do m1, 2, then I can combine that and do that combination with 3, or I can do m1 to m34 and then do combination of m1 2 multiplied by m34 and so on. Right? So what is the optimal way of computing the product? What is the optimal way of putting brackets, in other words? Brackets are what tell us. So when we say m1, m2, m3, m4, then one way of computing it is to do this, right? Do m1, m2, then m3, m4. Another way of doing it would be to say do m1, m2, and then do that multiplied by m3 and then m4, okay, and so on. So different ways of bracketing correspond to different evaluation orders for this multiplication. And what we want to do is kind of calculate without doing the actual computation, which is the best sequence in which to do this calculation so that we optimize the operations involved. So what is the inductive structure? So finally, when we do this, remember we can only do two at a time. So at the end, we must end with a multiplication which involves some group multiplied by some group. It must look like this. I must have this whole thing corresponding to some m1 prime, and this whole thing corresponding to m2 prime, and I'm finally multiplying m1 prime by m2 prime. In other words, m1 prime is for some k, it is from m1 all the way up to mk, and m2 prime is from k plus 1 up to n, right? So this is my m1 prime, and this is my m2 prime. And this k is somewhere between 1 and n. So in the worst case, I could be doing m1, and on the other side, I could have done m2 up to n, this whole thing. So this whole thing is my. The other worst cases, I could have done m1 to, not worst, but extreme cases, m1 to m minus 1, I might have already computed, and now I want to finally multiply it by mn. Or it could be anywhere in between. Right? So if I just pick an arbitrary k, then the first one has r1 rows, ck columns. The second one has rk plus 1 rows, cn columns. But we know that ck is equal to rk plus 1, so this matrix will work. So the final computation is going to be r1 into ck into cn, right? M into n into p. The rows into the column, common number of column and row into the final number of columns. So this final multiplication, we know how much it's going to cost. And to this, we have to recursively add the inductive cost of having computed the two factors. How much time did it take us to take m1 prime? How much time did it take us to do m2 prime? Right? So we have that the cost of m1 splitting at k is the cost of m1 to mk plus the cost of mk plus to mn plus the last multiplication r1 into ck into cn. So clearly this cost will vary for different k's, and there are many choices of k. As we said, there are n minus 1 choices of k. Anything from 1 to n minus 1 we can choose as k. So there are n minus 1 subproblems. So we did the longest common subsequence problem. We had two subproblems. We could either drop the first letter ai or the second letter bj, and then we had to consider two subproblems. We had no way of knowing which is better, so we did them both and took the max. Now here we have n minus 1 different choices of k. We have no way of knowing which of these k's is better. So again, we try all of them and take the minimum. There we were doing the maximum because we want the longest common subsequence. Here we want the minimum cost. So we choose that k which minimizes the split. And recursively, each of those things would minimize their split and so on. So that is the inductive structure. Right? So finally, we say that the cost of multiplying m1 to mn is the minimum for all choices of k of the cost of multiplying m1 to mk plus the cost of multiplying mk plus 1 to mn plus, of course, for that choice of k, we have to do one final multiplication, which is to take these resulting submatrices. So that is r1 into ck into cn. So now when we take this, right, so we have m1 to mn, so we have picked m1 to mk. Then as before, what will happen is that we'll have to split this somewhere. So we will now end up having some segment which is neither m1 nor mn. It starts at some mj and goes to mk. So in general, we need to express this quantity for arbitrary left and right points. We can't assume that the left hand point is 1. We can't assume the right hand point is n. Right? So in general, if we have a segment from mi to mj, then we want the smallest value of among all the values of k from I to j minus 1. We want the minimum cost which occurs from computing the cost of mi to mk and mk plus 1 to mj, and the cost of this final multiplication, which is ri into ck into cj. So this quantity we will write as cost ij. Cost ij is the cost of computing the segment from mi to mj, which involves picking the best k. Right? So mi to mj is called cost ij, and we use the same recursive inductive definition, choose the best k. So the base case, well, if we are just looking at a segment of length 1, supposing we just want to multiply one matrix from 1 to 1 or 3 to 3 or 7 to 7, nothing is to be done. It's just the matrix, there's no multiplication, so cost is 0. So we can then write out this cost ij equation saying the minimum over k of cost ik plus cost k plus 1j plus ri ck cj, which is the actual multiplication. And of course, I is always going to be less than or equal to j because we are doing it from left to right. So we can assume that the segment is given to us with two endpoints where I is less than or equal to j. So if I is less than or equal to j and we look at cost ij as a kind of matrix, then this whole area where I is greater than j is ruled out. So we only look at this diagonal thing. And the entries along the diagonal are the ones which are of the form I comma I. So all these entries are initially 0. Right? There is no cost involved with doing any multiplication from position j to position j along this diagonal. Now in order to compute I comma j, I need to pick a k, right? And I need to compute for that k all the values. I need to compute ik, and so it turns out that this corresponds to saying that if I want to compute a particular entry I comma j, then I need to choose a good k. Okay, and in order to choose a good k, I need, so this I can express in many different ways. Okay, so I can say pick. So for example, supposing I want to compute this particular thing, okay, then I have to say, okay, pick this entry I to I, and then I want the entry I plus 1 to j. So I have I plus 1 to j, this entry. Okay, so these two entries I have to sum up. Otherwise, I have to take this entry and sum it up with this entry. So in general, if I have a thing there, I'll say, okay, if I choose this entry as my k point, then I must add this entry to get it up and take this sum. Or I have to take this entry and add this entry and then add this, and so on. Right? So in general, we could have order n values I need to compute. For this, I need to compute, I need all the values here and I need all the values here. Okay? So I need something to the left and to the bottom, right? But if I start from the diagonal, then it becomes easy because I can actually say that if I have initially these values filled in, this is the base case, then to the left and below I can fill in this because I know its values to the left. I know this value to the left and below, so I can fill up this diagonal. Right? So in the next step I can fill up this diagonal because I have all the values to the left and below. Now this entry I have the values to the left and below, so I can fill up this diagonal. So I can fill it up diagonal by diagonal. So this is the order in which I can fill up this table using this inductive definition, because this is the way in which the dependencies go. So this is the code for this particular thing. So you can go through it and just check. The only thing that you need to note is that we have used some. So what we are doing is when we compute, as we said, one entry. So supposing we are computing this one entry, then we want to compute the minimum across many different pairs, right? This entry, and so on. So remember what we did when we computed the maximum longest common subword. We assumed that the maximum was 0, and every time we saw a bigger value, we updated it. Here we want the minimum entry. So what we do is we assume the minimum is some large number, and every time we see an entry, if it is smaller than the minimum, we reduce it. Right? So that's what's happening here. When we start the loop, we assume that the value for RC is actually infinity. Now what is infinity? Well, you can take infinity so that we can take, for instance, the product of all the dimensions that appear in this problem. You know that the total dimension will not be more than that. So you can take the product of all the dimensions. You can take a very large number. It doesn't matter. Something relative to what you have problem has. So we have not defined it in the code. But the important thing is that you're computing minimum. So instead of starting with 0 and updating it when you do maximum, you start with a large value and keep shrinking it. So every time we find a sub-problem which is smaller than the current value that we have seen, then we replace that value as the new minimum. So that's all that's important here. Everything else is just a way to make sure that we go through this table diagonal by diagonal. And for each diagonal, we scan the row and the column and compute the minimum across all pairs in that row and column. So as with this LCS problem, okay, we have to fill an order n squared size table. But the main difference between LCS and this is that in order to fill an entry in the LCS thing, we had to look at only a constant number of entries, right? So order mn or order n squared. But the point was each entry takes constant time, so the effort involved is the same as the size of the table. Okay, mn table or n takes mn time. Now here, unfortunately, it's not the case, right? So we saw that an entry will take time proportional to its distance from the diagonal. So in general, that will add an order n factor. So though we have order n squared by 2 entries actually, order n squared entries, we have to account for order n work per entry because each entry has to scan the row to its left and the column below, not just one entry away from it. And so this whole thing becomes order n cubed and not order n squared. So this is some point to keep in mind that there could be problems where the complexity is bigger than the table size, right? So all the examples we saw before, that's the reason to do this example. In all the examples we saw before, in Fibonacci we had a table which is linear in n and it took time linear n to fill it up. For the grid path and for longest common subsequence, we had tables which were n by n, but it took only n by n time or m by n time to fill them up. Here we have a table which is n by n, but it takes n cubed time to fill it up because each entry requires more than constant time. It actually takes time proportional to n.